A 24 billion parameter AI model scores 0.22 on a logical deduction benchmark. That's barely above random guessing. Someone copies 3 layers, pastes them back in, and the score jumps to 0.76. No training. No fine-tuning. No new data. Just copy, paste, done. That result should not be possible. And yet here we are. This is llm-circuit-finder, a tool built to explore what happens when you surgically duplicate specific transformer layers inside a large language model. The idea sounds almost too simple to be real, but the numbers are sitting right there in the benchmark results, and they're hard to argue with. So let's talk about what's actually happening under the hood, because this is not magic, it's a very specific exploit of how transformer models store and reuse information. A modern large language model is basically a stack of identical-looking blocks called transformer layers. Each layer takes a representation of your input, processes it, and hands it off to the next one. What researchers have started to notice is that certain layers seem to handle very specific tasks, things like logical reasoning, factual recall, or syntax. These are called circuits. And most of the time, they're buried somewhere in the middle of the stack. What this tool does is find those circuits. You give it a task, in this case, logical deduction, and it runs activation analysis across every layer in the model. It figures out which layers light up most strongly when the model is doing that specific kind of thinking. Then it duplicates them. Not the whole model. Just those 3 or 4 layers that are carrying the cognitive load for that task. The result is a model that is slightly larger, maybe 3 layers worth of extra parameters, but dramatically better at the target task. On the logical deduction benchmark, the jump from 0.22 to 0.76 is not incremental. That's the difference between a model that mostly fails and a model that mostly succeeds. And here's what surprised me most: the rest of the model doesn't break. General language ability stays intact. The model still talks coherently. It still handles other tasks. You haven't lobotomized it to boost one skill. You've just given it more capacity exactly where it needed it. But here's the thing, there are real limits here, and they matter. First, this only works if you can identify the right layers. The circuit finding step is not trivial. It requires running your target task through the model multiple times with activation logging enabled, which is expensive on a 24 billion parameter model. You need significant GPU memory just to load the model in the first place. We're talking about infrastructure that most developers don't have sitting on a laptop. Second, the gains are task-specific. If you duplicate the logical deduction layers and then test on, say, creative writing or translation, you don't get the same boost. You might even see slight regressions on tasks that compete for similar representational space. This is not a general intelligence upgrade. It's a targeted amplifier. Third, nobody fully understands why it works as well as it does. The hypothesis is that these layers act like computational bottlenecks. The model wants to spend more compute on certain reasoning steps but can't because the architecture forces it to move on. Duplicating the layer gives it a second pass. But that's still a hypothesis. The mechanistic interpretability research that would confirm it is ongoing. What could this realistically become? A few directions stand out. Imagine you're deploying a model for a specific enterprise use case: legal contract review, medical diagnosis support, financial risk analysis. These are all tasks where logical precision matters enormously and general creativity matters less. You could take an open-source base model, identify the reasoning circuits, duplicate them, and deploy a specialized version that punches well above its weight class on your specific task without paying for a fine-tuning run that could cost tens of thousands of dollars. There's also an interesting angle for edge deployment. If you can boost a smaller model's performance on a narrow task to near parity with a much larger model, you reduce your inference costs dramatically. A model that fits on fewer GPUs but hits your accuracy threshold is a real business win. The other direction is research. This tool essentially gives mechanistic interpretability researchers a new instrument. Instead of just observing which circuits exist, you can now ask, what happens when I give a circuit more room to breathe? That's a much more interactive way to study how these models actually think. So why does this exist at all? Because AI model improvement has been almost entirely dominated by one approach: throw more data and compute it training. More tokens, bigger batches, longer runs, higher bills. The idea that you could meaningfully improve a deployed model's capability at inference time, post-training, with no gradient updates has been treated as a curiosity at best. This project is a bet that we've been leaving performance on the table. That models already contain the circuits they need, and sometimes they just need more room to use them. It's a fundamentally different philosophy: find the intelligence that's already there and amplify it, rather than always starting from scratch. Is this going to replace fine-tuning? No. Is it going to work on every task and every model? Definitely not. But a jump from 0.22 to 0.76 with zero training cost is the kind of result that forces you to take it seriously. If you've been following this channel, you know next episode we're going deep into mechanistic interpretability, what it actually means to understand what's happening inside these models. If this layer duplication result made your brain itch, that one will too. Subscribe so you don't miss it.